All right. Welcome everybody. My name is Cesario Ramos. I'm working in Holland at a company called Cesario. It's a company specializing in agile software development and enterprise Java. I'm very happy to be part of this first PTJUG. My talk will be about Terracotta and how to use Terracotta to create lightweight grids, as I call them. I've been involved in Java since 1997. Since 2000 I started doing agile iterative projects, a lot of XP projects. Since 2004 I've mainly been doing agile coaching, guiding and coaching projects and teams in delivering better software. But I have a special interest in distributed computing and concurrent Java systems. The goal of this session is to give you an introduction to some issues regarding availability and scalability that we have in developing enterprise Java systems, and how a grid architecture could help you solve those issues. And after that we will talk about Terracotta and how Terracotta can help you realize a grid architecture. So this is the agenda: enterprise application challenges. How can a grid help in solving scalability and availability issues? Then we will take a look at Terracotta, and then we'll discuss a simple example that is based on a project we did about 2 years ago in Holland, in which we see Terracotta applied. And after that there's questions and answers. We have a relatively small group, so we could do questions during the presentation. I will try to reserve 5 to 10 minutes at the end, so we can discuss some issues. Okay, application challenges. Well, since the internet era arrived, availability and scalability have been very high requirements. And for example, a web shop, we want a web shop to be up 24/7. For example, Amazon wants to sell books every minute of the day, for all days of the week, all weeks of the year. Even if, for example, payment verifications can be done, they want to sell books. They will check payment verification later on. So availability is a high requirement, and how can we achieve high availability? Well, we have to eliminate single point of failures in our architecture. If you don't have any single point of failures, then chances are that our systems will expose high availability. Scalability is also an issue, and scalability has to do with adding hardware, and the result of that hardware, adding of that hardware, would be to be able to handle more requests. So if you have one server handling 10 requests a second, and you add another box, then the result should be, well, you would be able to handle 19 or 20 requests a second. If you only have an increase of 2 requests a second, then you would say, okay, this is a very bad scalability. And we can make our system scalable by avoiding single points of bottlenecks. So a little bit more about high availability. So it's obvious that if we add hardware, so if we have one box that has 99% uptime and we add another box with 99% uptime, that the uptime increases 99%. The more interesting thing is, if you add tiers, so for example, if you have a web tier and you add an application tier and then an enterprise information tier, doing that actually decreases your availability. It's quite interesting to note. So you should take that into account. Another thing is, it's often better to have multiple smaller machines and fewer big machines. Because if one machine goes down, then the load is spread among more machines. So if you have two machines, for example, two 4 CPU machines, if one goes down, the other machine should be able to handle twice the load. High scalability. So one thing to focus on is the co-location of tiers. If you can put the web tier and the application tier in one box, that's good. It's a good thing to do. You reduce costs of communication, costs of remoting. Other thing to focus on is concurrency control bottlenecks. Using isolation levels, for example, in databases, you should always try to use the lowest isolation level. And you also, if you have critical sections in your code, you should minimize the time spent in those critical sections. And it's very bad practice to, for example, access a shared resource while holding a lock. Okay, so and if you have, if your architecture eventually will come up with a bottleneck, then it should be that bottleneck should not be in the more expensive tiers. So it should be in a tier as high as possible. So, for example, it should not be in the database tier or in the integration tier. And we will see a reason for that in just a moment. And to achieve high scalability, you could use caching for fast data access, so for accessing data right in memory, and for unloading those expensive tiers. Okay. The client-server architecture is an architecture that is well known and that we use a lot. And if we draw it like that, and the load starts increasing on our server with our database below, then it's obvious that we have introduced a single point of bottleneck and a single point of failure. So the obvious thing to do is, well, let's cluster the application servers, the web servers. We arrive at a picture like this. So we have our clients, and our clients access our web farm using a load balancing router that distributes requests through all those servers, and all those servers use a database to access data. And well, what happened is that when we went from the one server architecture to the multiple server architecture, is that a lot of issues were introduced. We now have to take care of, we now have to worry about distributing state among all those servers. If you are putting stuff into your HTTP session, we have to worry about, okay, what is the load on my network? What is the load on my CPU for deserializing and serializing my object graphs? I have to take that into account. So one thing to do is, okay, let's keep our HTTP sessions very small. For example, 10K kilobytes or 5 kilobytes. Another thing you have to worry about is, what if one of those servers goes down? What will happen to that request? So the obvious thing that you could do in this kind of architecture is to put transient state into the database. So a request comes in, you put transient state into the database. For example, when buying a book, you follow a certain workflow, and that state you put into the database. When one server fails and your second request comes in, the load balancing router chooses another server, and then that server can process a request because it can find your state in the database. Very obvious stuff. But what you're doing is that in this case, you're unloading unnecessarily responsibilities to your database. You are unnecessarily creating load on your database. And if you have high load systems, eventually your database will become bottleneck. Then you have a big problem. The problem is that clustering a database, for example, is much more complicated than clustering a web farm. And not only that, clustering a database is also much much more costly clustering a database. And if this is a mainframe, then problems are even higher. I spent a few months ago, I discussed I had a 30-minute discussion with a guy, with a mainframe guy, because the guy had 2 CPUs in the mainframe, and we were having load problems. And in that half-hour discussion, I was just telling him why not add another CPU to your mainframe? It can't be that hard. Just add another CPU, and then, well, everything goes well then. But after half an hour, he finally got to me, and the problem was that adding a CPU to a mainframe costs about 1 million euros. So it's not that easy to do. So, but it took a half hour for me to understand what he was trying to say. So, and the same thing could apply to service-oriented architecture. On service-oriented architecture, we have a lot of tiers, and the same you can run into the same problem. So to summarize this intro on availability and scalability, we must try to avoid single point of failures, single points of bottlenecks. Don't misuse your enterprise information systems for transient data, and caching is a very good and often underestimated solution for using in your day-to-day enterprise Java systems. Okay, any questions so far? Is it clear what I'm saying? Should I slow down, speed up? Not that much reaction? Now we're going to take a look at the grid approach. So how can a grid architecture help us solving these issues that we discussed? So what actually is a grid? Well, everybody knows a grid, namely the power grid. Power grid that takes that brings electricity to our houses is a grid, and it is made up of power stations and power substations, and all those stations are interconnected via electricity net. And the idea is that if one of those substations or stations fail, then we won't notice. I know that isn't true, but that's the idea. Because, well, the electrical network is also redundant, etc., etc. So you can, if one power station goes down or one part of the network goes down, you still have power. So the same thing applies to a computational or to a computer grid. It's just a number of nodes, a number of boxes interconnected via a network. So this is a picture that I chose to display it. But the world in our day-to-day work is mostly just our IT department or our company. It's not the entire world. But the idea is that in a grid, you can put work into the grid space, and then the grid middleware takes care of distributing your work to the nodes. And just as in a power grid, to me as a consumer, I just want electricity, and the power grid is just one big resource of electricity. In a computational grid, for me as an application or a user, the grid is just one big resource of computation. So I put work in there, and then the work is distributed using the grid middleware to all the nodes, and then the grid middleware collects all results and gives the results back to me as an application or a user. So this approach gives you no single point of failures, because we have any number of nodes and all the nodes are in the same tier. And it gives you high scalability, because you can just add a new node and then the node gets registered in the grid and can take up work. So we have scalability and we have availability. The problem with a computational grid is that in day-to-day enterprise Java systems, we don't have computational problems. We always have problems that have to do with data access. So the increase in computational power that we get from a computational grid is limited by the data access speed that we can realize. Because the work that we have to do in one of these nodes will require access to data. So it is bounded by the computing power is bounded by the access to data. So, to cope with that, there is another type of grid called a data grid. And in this data grid, what we do is, well, we have, using distributed caching techniques, we just put data in memory on the nodes. And once we have that, the work that we distribute to those nodes can access the data locally. Well, that's the approach taken in a data grid. And a data grid is, in this approach, is therefore very usable in our enterprise Java systems. So, caching topologies. So, in those data grids, we can choose. There are a number of caching topologies. These are the two most known: partitioned and replicated. In a partitioned topology, what we do is we just divide our data set into sets, non-overlapping sets, and then put on each node a part of that complete set. And if we do that, we have very high scalability, because if we add one node to the system, it gets a non-overlapping part of the total set of data, and the other sets of data minimize, become smaller. So you have the memory added to the grid is it's just the memory that you added. It's very good. And what you get also is load balancing, because if we assume that the requests arrive in a uniform distribution, then the requests are just, every server has the same amount of load, the same amount of work to process. Replicated topology means that instead of partitioning our data, we just put all data on all nodes. And the advantage of this is that you get very, very, very high performance, because you can access all your data in memory from every node. There's a problem. If you have to do updates in this architecture, then the problem is that every update must be distributed to all nodes in your network. So this replicated topology is only suitable if you have low number of updates in your application. So to summarize, availability and scalability in grids. Availability is realized because of data duplication and redundancy in machinery. Scalability is realized because you have in-memory data access, and the dynamically allocation of resources. But that is also a problem. It's also a thing for availability. And the grid middleware takes care of dynamically adopting new nodes. Persistence is a good point. It takes care of persistence. So if you put work into the grid and while processing it, the system fails, then the grid middleware just finds a new node to execute the work on. So it offers you persistence in the data that you put into the grid, or the number of work that you put into the grid. And normally, grid middleware also takes care of transactions. So you could do, in the case of a replicated topology, a update among all nodes, and then only commit the update if all nodes agree on the update. So okay, this was the introductory part. Are there any questions so far?
You also have kind of a hybrid topology where you partition, and every partition is a small cluster, right? It's also using coherence, this kind of.
Yes, in time-of coherence. Mm-hmm. Yeah, of course. Yeah, you could have a partitioned L1 cache, as they call it, and then a replicated L2 cache, or vice versa. So there are a lot of. It's a whole different topic, but there are a lot of issues, a lot of ways to configure your caching. But these two are the two basic ones that I wanted to discuss.
I was stopping just because of if you have a partition with where the partitioning node is only a single computer, and if it fails, it becomes a single point of failure. And if every partition is a cluster, then you have the advantages of.
Yeah. Okay. what you're saying is, this is all the data is partitioned here. So data A is, for example, all persons starting with the name, all names of persons starting with an A up till D are in this data, in this node. If this node fails, then yeah, we can't process any requests for those guys. That's what you're saying.
Yes.
Yeah, but the grid middleware, Coherence, for example, has for every data, it has a backup node. So this is the primary owner of the data, those persons, but also there's always another node that has a backup of that data.
Kind of hide system.
Sorry?
Like on the hard disks when you have a hide system and there is some replication of that.
Yeah, for example, yeah. Okay, so let's go to Terracotta now. If I'm not mistaken, I'm 25 minutes away. 20. 20, okay. That's good. So Terracotta. Terracotta, who of you guys have worked with Terracotta or know about Terracotta?
Well, I knew about.
Okay. You have also worked with Terracotta in real life situation? Okay. So okay, Terracotta, what is it? Terracotta is a open source framework. Terracotta, the company, made open source, if I'm not mistaken, about 1.5 years or 2 years ago. And what it does is it provides you with a basis for realizing availability and scalability of your Java systems. And it does this by clustering your JVM. So you get a clustered JVM. So what does that mean, a clustered JVM? So it means that, for example, if you have an object in one JVM, on one heap of JVM A, and another JVM wants to access that object, then it accesses the same object. So, well, I'll come back to that, to this little word of scaling at the JVM level, what that implies. So, it allows you to write Java applications, so it allows you to write concurrent Java applications for one JVM and have them execute them on multiple JVMs without any modification. So, it reduces the complexity of distributed computing, and it does all of that without providing an API. So there's no API to program to. So, for example, if you're using a caching solution or something, or you're using RCP or RMI solutions, there's always an API that you have to program to. Well, when you use Terracotta, you just program your Java application using POJOs, and if it is a correctly working concurrent program, then it works correctly on multiple JVMs. Okay. So let's take a look at the Terracotta architecture. Well, the Terracotta architecture is what you see here. One important thing is this Terracotta server here. This Terracotta server provides your JVMs with an extended heap, an extended persistent heap. So what this means is if you have a application running, for example in this app server, in this JVM, then just like paging of your operating system, paging in and out of memory from disk to memory, the same thing applies for the Terracotta server. So you could have a heap that is only bounded, it's only bounded by the disk capacity of your Terracotta server. So if you're accessing objects in your JVM, or creating lots of objects in your JVM, when this heap of this JVM fills up, it just starts paging JVM objects, heap objects, through the Terracotta server. And next to that, you can connect any number of JVMs to that distributed shared heap. And those objects have cluster-wide unique IDs. So what I was telling you about, if there is an object here called person with a name, I don't know, Frank, and you call a method setName on this object, in this JVM, it is also updated on those other JVMs, transparently. You don't have to do anything about it. And it's only updated in those other JVMs if it is actually on the heap of that JVM. If it's not, then it's not updated in that JVM, it's just updated on a Terracotta server. So this gives you the possibility of creating high available and high scalable systems. So the Terracotta server is no single point of failure because it can have any number of backups. So just not a single point of failure or a bottleneck. So what kind of objects can we put into this this extended heap? The things that we can put in there are called distributed shared objects, a term that Terracotta invented. And you have to define using point-cut expressions, using aspect-J, aspect-oriented technologies, which objects you want instrumented by Terracotta. And when Terracotta, when your JVM starts up and classes are loaded using your class loader, it starts instrumenting those classes at various specific points. For example, it starts instrumenting the bytecode of your classes at the constructor level. So if one app constructs the object here, then if that other application wants to construct the same object, then the constructor isn't executed because the object is already created once. It starts inserting bytecode into the monitor locks, into the monitor acquire operations, and into the lock acquire operations, and into the lock release operations. It starts injecting bytecode into the, for example, the setter and the getters of objects, so that it can take care of distributing your objects. And okay, that's what's here, what's depicted here. So an object to be distributed must be instrumented by Terracotta, and they also introduced the concept of a shared root. And those shared roots are objects that are the roots of any distributed object graph. So, and this is the only place in which Terracotta violates your normal Java JVM semantics, because a shared root is statically across JVMs. So you create a shared root, you set some data members. If your JVMs all go down and the JVMs come back up and connect to the Terracotta server, then the shared root is still there with the same data. And also all data that is referenceable from the shared root is also still there. But you can remove that data if you remove it in your application. Then it's removed from Terracotta server also. But the shared root can never be removed. So okay, as I already said that, I didn't say this. So for data to be distributed in your cluster or in your grid, they have to be inside a Terracotta transaction. And a Terracotta transaction is demarcated by a lock acquirement and a lock release. So for example, an ordinary synchronized block in Java, when you enter it, you get a lock. When you leave it, you release the lock. The data that is changed inside that synchronized block is synchronized to your cluster where needed. Okay, so Terracotta, how does it realize availability and scalability? So every data that is written to Terracotta space remains there. So you can crash as a processing node, but after that your code is still there. You have redundant TC servers, so Terracotta servers can be redundant, any number of Terracotta servers. You have fine-grained changes, so there is no serialization involved here. So, for example, if you just cluster using JBoss or WebLogic or whatever, what happens is that your object graph gets deserialized and serialized when transferring data across clusters. Well, that's the thing that has a very high impact on your performance and on your scalability, etc. What Terracotta does is it only distributes the actually changed data. So if I have a person object and it's changed its name, only those 4 bytes, for example, are distributed. Not the whole object. Person is serialized in everything that is referenceable from there. All right. And one other thing to point out is that if you have Terracotta, Terracotta will take care of automatically partitioning your data. So it will only move data to a JVM if the JVM is actually needing it. So if you have an application that only works on data of a particular set, then Terracotta just optimizes data to that particular node. And only that data. So updates of other data are not distributed to that node. Okay. Well, enough theory. Let's look at a very simple example of a producer and a consumer. You see a consumer that has a linked blocking queue. A linked blocking queue is just a queue from Java util concurrent. It has a put and take. And if you put something in it, it blocks. If it's full, and if you take it, it blocks if there's nothing in it. So the consumer just has a while loop consuming things, and the producer has a while loop just putting things in there. And yeah, normally this thing wouldn't work because if you start it up in 2 different JVMs, well, this queue isn't the same as that queue. But with Terracotta, you can define in the Terracotta config file that those roots, those queues are shared roots. That's what we do here. We have a root name, a root queue, and the field name is producer.queue. The same holds for consuming.queue. So when we start this system in with Terracotta, those 2 objects share this root, and every action performed on that queue is visible to the other JVM also. So what you can do is you can start up any number of consumers, any number of producers, and they all share the same queue. So your code is just you're just writing a normal concurrent Java code for one JVM. Terracotta takes care of distributing it across multiple JVMs. Okay. So Terracotta use cases. Where could we use Terracotta in our day-to-day work? Well, we could use it for making a data grid or a computational grid. And there is even a official specification made by Bea and by IBM. It's called the Work Manager specification. And it allows you to create a master worker grid in an easy way, and it is supported by IBM application servers and Bea application servers. You could use it just to cluster your POJOs. One thing that we did in a project, for example, we were working for the Dutch National Railway, and they were putting on all stations in Holland, they were replacing their screens from old screens based on mechanical stuff to digital displays. One thing that we did, in this case was, well, we have to, those screens have to show information, traveling information. So we had that traveling information on our grid, in our grid middleware, on our grid servers, and each of the screens just using Terracotta would get the data that it needs from Terracotta server. So station, I don't know, Amsterdam only is interested in the data of Amsterdam, and the data is just available in the grid, but only those screens, those JVMs in those screens that access the data of Amsterdam get notifications, have to do with the screens, the data of Amsterdam. That solution we used for the whole of Holland. So that's an example of clustering PTJUGs. Another thing that you could do is distributed caching, using standalone caches, for example, or using it as a Hibernate L2 cache. I don't know if anybody is familiar with Hibernate L2 cache. That's the thing you could do. But the other thing that you could do is cluster Spring with it, so that your Spring beans are clustered. And a very obvious thing is HTTP session clustering. And the benefit of using Terracotta for HTTP session clustering is that it doesn't use any serialization. And your object graphs in your HTTP session could be a lot bigger than when you're using serialization. So we have availability and scalability at the JVM level. If you use Terracotta, you can develop such a solution. You keep JVM semantics across the cluster. Your application is just the way it should be. And well, this is the point I want to make. You can easily use it to create your grid architectures. It's very easy to do. I still have 5 minutes, I guess. Yes.
Yes.
So what we could do is we could do questions and answers the last 5 minutes, or I could discuss a.
Okay. It's not a normal JVM, right? It's not a vanilla JVM downloaded from Sun.
Well, you could use the IBM JVM. You could use the JVM from Bea. JRocket, yeah, that's now included. You could use all JVM from Sun.
Yeah.
Not all, but the latest ones. I guess it starts with JVM 1.5 or something. It's already supported. So what Terracotta does is it modifies your class loader. So it has its own class loader. And when you start up the JVM, you have to put in a different YAR, different class loader. And that class loader reads the Terracotta configuration file, and then based on those point code expressions, starts instrumenting the classes that are loaded. So yeah, you could not use any JVM. You can only use the supported JVMs. Yes. But the main ones are supported.
Any points against Terracotta? Any downfalls?
Yeah, there are some downfalls. For example, not every object can be a distributed shared object. For example, if you have objects that are locally to a JVM, for example, a file thread or a thread, well, there's no sense in clustering that. A file on one node, yeah, it has no meaning on another node. And for example, not the complete Java util concurrency library is supported, only a very limited set. And there are other classes that are not supported too. But by supported, it means that you get it out of the box. But you could implement those objects yourself, and then they could be distributed using Terracotta.
So actually, it's easy to adapt an existing application to use Terracotta, but it's not always straight. It's not always just installing Terracotta. Right?
No, it's not always like that. No, if you are using, if you have an existing multi-JVM application, then you have to do a lot of configuring. For example, those things like a file or a thread that can't be distributed, well, you must exclude them from being instrumented.
Still, I read something about adapting Tomcat to serialize the sessions via Terracotta in 1 day or so, and they also did something like that to enhance cache. EH cache, I think.
Easy Hibernate cache is to make it easier for you to write applications and use Terracotta on that. They already ported some of the basic frameworks. For example, there are 4 or 5 caching solutions that are already Terracotta enabled, so you can just use them. If you were using Hibernate cache, Easy Hibernate cache in your Hibernate systems, well, you just plug in the Terracotta version, and then you have Terracotta cluster, which is much faster and performs much better. So there are a number of standard frameworks and standard application servers that they already converted for you, that you can use in your system.
Are there any security issues?
Are there any security issues?
System vulnerabilities that can happen with the use of Terracotta?
Security, you mean attacks?
Exactly.
Malicious attacks? Well, I don't think that using Terracotta introduces any additional security vulnerabilities than when not using Terracotta. I think if you're using a grid or a clustered architecture, then you have to make secure connections between those nodes. If you're using Terracotta or not, that doesn't make a difference. And security in the sense of failing work. So you distribute work, it is executed on a node, and then the node fails. Well, that is something that Terracotta offers you support with, because every data is persistent, as we saw. And next to that, it doesn't offer you anything, but you'll have to develop it yourself if you have special requirements for it.
I'm curious. You talked about for the train company, the notifications on the screens. You used a queue like in your example before, or how does Terracotta help you propagate notifications?
No, one good question. One thing. Did everybody understand the question?
Yes.
Okay. Well, a good question.
That's active versus passive as in the data.
Yeah. Well, with Terracotta, you don't. The problem that you're slicing here is, if you don't use Terracotta, you usually want some kind of caching strategy or something, your domain model gets broken. Because if you get a person from cache 1 and another JVM or another thread gets the same person from that cache, semantically they are the same person, but if you do an equals operation on them, they're not the same person. If you set the name of this object, it's not it's not directly updated in that one. So if I update this one, then I have to synchronize it with the cache. And then the other one, after he does updates, he has to check. Is there any updates done by other processes, etc. So that it gets complicated. So to get back to your question, we just have for each screen is just an object. And we have an object screen, and that object has data on it to display. So that data is just displayed on the JVM that uses that object.
And you just poll that data. It's polling them.
No, it's live. I have a screen object that I display.
Yes, but how do you know that the screen changed?
Because object changed.
And how do you know that the objects, you have to poll the object so on?
No, I don't have to poll object. I just have an object that I'm displaying, and if I call set name on that object, then the name data, the name property changes, and then that's displayed.
And you can have active code on the setter, is it?
Active code on the setter?
I don't know if I'm explaining. How do you take action when the data change? So to render the data, to refresh the data, to tell to the screen to print the data, how are you notified? Do you simply keep repeating, keep checking the data, or does Terracotta give you some kind of notification mechanism, or can you have code in the setter for that object that is called when a change happens?
You could have that also. You could have if you use Swing, for example, you could do that. You could do listener stuff. You could register a listener when I do set name, then that name.
And the listener is called.
Then the listener is called and the view is updated. You could do that model view controller, but we didn't. we can discuss this after because I'm running out of time.
Yes,
I already
2 minutes.
ran out of time.
You thought that the data put into the grid is persistent. Is there some kind of persistent store behind the grid? So if the grid, all the grid goes down, when it comes back up, does the data that was put there is it still okay? Is it still there?
Okay, let me. This is the last question. Yes, you could do that. Let me just go back to this picture. So which grid do you mean? This grid of our grid nodes or the infrastructure grid?
Basically everything.
If this goes down, everything goes down.
Yeah.
So if this and this goes down, you can run Terracotta in persistent mode. And what this means is that the heap, the extended heap here is persisted on disk. But that's not very good for performance. So, okay, then we can discuss later. During beers or something. All right, thank you.